Okay, cool. So, hi everyone. Let's just finish the exam review. There's like 2 pages left. I think we can get through it. Before I start, these problems are okay. There's nothing else specifically you had questions on, right? It's okay if we just finish this? Okay. So this problem, what are we given, and then what are the reagents going to do to it? Yeah, you got an aldehyde. So that is going to make an acetal. So what happens when you have an aldehyde or ketone and then a diol like this, you basically just imagine each end of the alcohol like attaching itself to the carbonyl carbon. And then you attach those two oxygens and cut off the carbonyl and the oxygen. And then you get your cyclic acetal or ketal. And what is the point of this? Like usually in reactions, why do we use cyclic acetals? Protecting groups. Because carbonyls are reactive, and if we don't want to react with a specific carbonyl, we can just protect it with an acetal. So cool. This product turns into the same thing, except now you have an acetal. Okay. And then what else do you notice about this specific molecule? Like besides an acetal, what functional group is on it? The PPH3. So that tells you it's a what? It's a Wittig. And there is a double bond here between the phosphorus and the adjacent carbon, which means that it's a reactive reactant. So when you have an R group and a PPH3, it's called your phosphorus ylide. But in order for the phosphorus ylide to actually do something and react, you need this carbon right here to be deprotonated. And that'll either be represented as like a a lone pair on the carbon, so like a carb anion, and then a positive on the phosphorus, or just a double bond between them, which neutralizes both of them. So you need to make sure it's reactive before you actually do the reaction. If it's not reactive, make sure that there's some kind of base in solution. All right, so we've established that this is an ylide, and then what does the last step do? Yeah. So now when you have an ylide plus an aldehyde or ketone, all you do, chop off the O, and then I take the R group that starts like on one end of the double bond. So ignoring like the phosphorus stuff, I'm just going to count this R group starting from like the carb anion. And then I will literally just take that and transplant it where the oxygen used to be. So this carbon right here is going to replace the oxygen, and then you get the two R groups mashed together. So in your final product, you have the two methyls from the, what do you call it? The ketone. And then you have the R group from your ylide. And you're just cutting and pasting, so it looks like that. Okay, so next, what do we have? What does it do? It does make an acetal. So to make a cyclic acetal, you need to identify two ingredients, aldehyde or ketone plus diol. In this case, they're a little rearranged, but it's the exact same thing. You have a diol here, you have an aldehyde or ketone. These two are just floating around in beaker soup. When they combine to make a full acetal or a cyclic acetal. So like, yes, the aldehyde is on the reagent line, but it's the exact same deal. So you take both ends of the oxygen, attack the carbonyl carbon, cut the rest off, and then you get cyclic acetal. So the R groups from the carbonyl, they stay the same, but we have this new protecting group up on top. Yeah, and this is something you'll need to identify. Like, as long as there is a diol or a carbonyl somewhere, even if the diol isn't like traditionally the one you've seen, like this, it's still going to go ahead and do this reaction if it's given an aldehyde or ketone. Okay. So now, yeah. So the next one, what's gonna happen? Yeah, you get an aldehyde because you have a primary alcohol, and then you have PCC, which is a weak oxidizing agent. So if you do PCC oxidation on a primary alcohol, it can't go all the way to a carboxylic acid, so it stops at aldehyde. So after you get your aldehyde, you're giving it excess methanol. So what happens now? So alcohol plus, what do you call it, a carbonyl. You just add the alcohol onto the carbonyl carbon, you get acetal, ketal, whichever one. So methanol, we have excess methanol. So we know that it's going to go all the way to a full acetal. It's not going to be like a hemiacetal with just one methanol attached. So we have our methanol, just go in, attack the carbonyl, oxygen gets cut off, and you replace it with new groups. Okay, so we have a nitrile, and then this reagent, what's it called? What does it do?
It's a grignard, yeah, and it attacks the carbon.
Yes. So when you have a nitrile, the C triple bond to an N, and you give it a Grignard, what happens is that it turns into a ketone. So this carbonyl carbon, like a carbonyl derivative carbon of the nitrile, is electrophilic. So we just cut off the MGBR, turn into a lone pair, and then attack that carbon. So in that attack, you add another R group to that carbon. And then in the second step, when you do some kind of acid or water workup, the N just gets replaced with an O. So we have our original R group and then the one we added with the Grignard. So we have one more methyl and then the oxygen on top. So So nitrile plus Grignard equals ketone. Okay, next. Yeah, what's the product of that reaction? Like go up on top here? It would, but this thing in the middle makes it a carboxylic acid derivative, which makes it reactive enough that you can do nucleophilic acyl substitution. You form an amide, yeah. So when you have a carboxyl derivative that's fairly reactive like an anhydride, and then you give it an amine, and the amine can be like as ammonia, primary amine, or secondary amine. But what you know happens is that the amine just goes in and attacks one carbonyl, and like this whole thing just hops off as a leaving group. So then this gives you an amide, which is another carboxyl derivative.
Can you show the leaving group too?
Yeah. So I think it is actually going to be the ion.
It would need like H2O to formulate it, right?
Yeah. So I think what happens, well, I'm pretty sure this is what the textbook says, but for acid anhydrides, if you like cleave them with an ammonia, you get the oxygen and it's like still deprotonated, but to satisfy the charge, you have it ionically bound to NH3.
If you had H2O in the solution as well, would it just protonate it?
Actually, I think it would be NH4. Sorry, yeah.
If you had H2O in the solution as well, would that just protonate it? And then it would just be.
Yeah, I think that would just quench everything and you wouldn't have, like, you wouldn't need to form the salt.
Yeah.
So I'm not sure. I guess that's why Dr. Roche isn't too concerned with the side product.
Alright.
He's actually not too concerned with acid anhydrides in general. The main thing he wants you to know about anhydrides is like the Friedel-Crafts thing, like how they can go to Friedel-Crafts acylation. Okay. So we have a molecule, there's an ester on either side. What do these reagents do to it? You just hydrolyze it. So every time you see this stuff plus an ester, you know you're just going to do hydrolysis. So I don't even know the mechanism, but let's say the NaOH attacks, and then you have like each alcohol is a leaving group. The point is, oh, on both sides, because I guess this is assuming excess, because they didn't give you like a quantity. So yes, you're just going to go ahead and cleave both sides. And then the leaving group, you get 2 equivalents of ethanol floating around. Yeah, that came from the ester leaving group. Okay, what is this? Okay, so I gave you the first and last step and the intermediate, and I'm asking you to find the reagents. So yeah, take a minute to find the reagents. Oh, what? Not isolation, because the transformation, you're going from an acid chloride to an ester. It wouldn't be Williamson. Because you wouldn't need to. There's no alcohol present in the first one. CH3ONA. Yeah, you could. Any nucleophile that has like the appropriate OR stuff. So as long as you attach this in the end, that would work. So you could use like methoxide, which would be CH3ONA, or you could use just like methanol, which is what I used. So I'm just going to use methanol because for all these reactions, all these nucleophilic acyl substitutions, if you're given a problem like this, where you have the first and final product and you have to find out like what nucleophile you attach with to get the final product, I just find the thing that's attached to the carbonyl, detach it, and then add a hydrogen on it. And then that's like your answer. Because this entire chapter is replacing this leaving group on the carboxyl with other stuff.
And then NaOH, like previously.
NaOH for the next one?
Yeah.
Yes, exactly. So we have an ester in this step, and then carboxylic acid in that step, which means we just hydrolyze the ester. And then for hydrolysis, the reagents, you're right, are NaOH, H2O, and acid on the bottom. It's like all forms of water.
If you just had water, is that gonna go to carboxylic acid? Just had water for the ester?
No, I think you need some kind of catalyst because it's not reactive enough. I think you could do it without the NaOH as long as you have like the H3O at the bottom to push it forward. Let's see. Okay, so kind of the same deal with the next problem. I gave you all the reagents and you need to give me the product. And I do kind of need to fill time here, so I'm gonna ask one of you to give me the answer, like just draw it up. Huh? Yeah. Wait. Yeah. To a ketone?
No. It's an acyl. Or
Yes. So PCl5, it goes to an acyl chloride.
what?
In what? Yeah. Yeah, so now we have acid chloride, pretty reactive, nice leaving group. We just take the amine, attack the carbonyl, chlorine leaves, and then you get an amide.
I'm using that stuff.
Mhm. Oh, okay. So in this transformation, what was the missing reagent? Carboxylate ion, no. I mean, possibly, but no. Mhm. So if you want to go from carboxylic acid to an acid anhydride, you react it with the appropriate acid chloride. So when you give it the acid chloride, in this case, we're going to use this one. You can go ahead and attack with the carboxylic acid like this. And then you get the O in the middle. They're joined as an acid anhydride. And huh?
It's more simple than,
The carboxylate ion.
yeah.
It's not, yeah, not really simple. It's just like more viable as a reaction.
Yeah.
Yeah, we know for chapter 17, we just have to cut and paste nucleophiles. So in this case, we started with this group, and then we had to add this. So in this case, we already had our nucleophile as like the carboxylic acid because the oxygen is attached here. And we know it's like from this side because this is an acetic acid and this is the acyl group. So we know we had to add this side as like the other half of the reaction. So I turn into an acyl chloride because that's more reactive and the carboxylic acid can go in and attack it really easily to form that molecule. And it also works backwards. Like if you were given the acid chloride and then the final product, you'd have to give them the acetic acid as the missing reagent. Okay, anyways. Next. What happens?
Go back. When you said that you want to go back to it.
Yeah.
Anhydride, when you choose.
Oh no, like if it was switched around, like if you were given the acid chloride as your initial reagent.
And to go from the anhydride to carboxylic acid, just water.
Like to break a carboxyl derivative to get another derivative, you just use like the nucleophile you want to attach. So to go from any of the derivatives to carboxylic acid, you're going to use water as a nucleophile because you attach the OH in the end. Same for ester, like you would use an alcohol to hydrolyze it because, or to break it because you want to attach the alcohol in the end. All right, so what happens here? The carbonyl, what part of the carbonyl? Yeah, it's going to replace the oxygen because this is a ketone. There's no leaving group. You're not going to have anything to like substitute. So what functional group does this form in the end? And not an amide, the enamine. So you know it's an enamine because this is an aldehyde or ketone, and then this is a secondary amine. Aldehyde and ketone plus secondary amine, you get an enamine. So what does the final product look like?
The double bond on the left side, that's still the double bond. And replace the O with the N and two R.
Yeah. So to make an enamine, whenever you see the reagents, cut off the oxygen, cut off a hydrogen, put the N where the oxygen used to be. Let's see. But now you need to put a double bond somewhere to satisfy this carbonyl carbon. We can't put it on the nitrogen because that would be bad. It would have a charge and we don't want that. So we're gonna put it on the sides, like one of these alpha carbons of the carbonyl. So you have to determine which side to put it on. And we said put it on the left side because that's the only possible place to put it. In order to get a double bond, you have to do an elimination reaction where you have some kind of thing coming in, taking the hydrogen, and then the electrons from the hydrogen bond go up to make the pi bond. So if you don't have that hydrogen, you can't make a double bond there. So ideally you'd go with the most substituted side, but the most substituted side with a free hydrogen, which happens to be the left. Also, please do memorize all the functional groups and what they look like in different situations, because I think those are some like easy points if you know them. All right, next. Yes. So PCl5, cut off OH, add a Cl, you get acid chloride. And any specific place, yeah. No directors, no directing effects, just add it wherever. And last step, into what? So reduction into secondary alcohol. If you were reducing with something like a Grignard, it would be reduced into a tertiary alcohol.
We would add like AR.
So you're just adding an H for this. All right. So what reagent is missing here? Yep. You just have to memorize, this is cyanohydrin formation. You just have to memorize aldehyde plus ketone plus HCN gives you this thing called a cyanohydrin. Okay, so benzene and anhydride, what happens?
I forgot what the name of it is, but it's gonna form like the boat. Right?
The boat?
Like the benzene to oh, it's like.
Yeah. Well, so technically what happens is that like one of these carbonyls attacks the catalyst and then it opens up on its own, but that's dumb. So we're just gonna draw the arrow, like you said, to attack the anhydride. So on the anhydride, we have two carbonyls, literally just pick one, and then you draw an arrow to attack it to open it. But you have to look at the directing effects on the benzene to see where you attack from. So which carbon are we gonna attack from? Yeah, either one of these. The methyls are ortho-directing and symmetrical, so it's the same thing. So let's just attack the anhydride. Once it attacks, just open it up and then you get your acyl group attached onto the benzene. And last step,
Reduction.
yes. And then what gets reduced?
Oh,
Everything gets reduced. Lithium aluminum hydride is the strong reducing agent, so reduces aldehydes and ketones and carboxylic acids as well. So that's it.
is that gonna form the alcohol? Secondary alcohol?
But you were, oh my God, yeah, you're right. Okay, yeah, that was dumb. So lithium aluminum hydride does not reduce it to alcohol. That's Wolff-Kishner. It reduces it to primary and secondary alcohols. These like lowest degree of alcohol possible. It's just the catalyst for it. It's not important. Cool. Very last one. So overall, what kind of reaction is this?
I'm not good with the names, but I know that that's.
It's Wittig. And there's two missing steps. What are the missing steps? The missing steps related to forming the ylid. So yeah, just find the intermediates using that reaction. So what do you think you need here to get all, or like just to fill this out? Like what's missing?
The part,
The alkene part, yeah.
the phosphorus,
And then what else? We got the ketone right here. So these steps in the beginning are to prepare an ylid to react with this aldehyde. So now how do we prepare the ylid? Yes. You do activate it. But what do you need to get the non-active form first?
has to the alkene.
Yes, you're gonna need alkyl halide. But how do you know which alkyl halide you're starting with?
Yeah.
Oh no, not like the halogen. Like we're concerned with the R group. It could be any halogen really. So how do you know which R group to put on the alkyl halide?
Using everybody, so the top part is, once you see the bottom of the side, that
Mhm.
means that the other side has to be formed.
Exactly. So in the final Wittig product, we find the double bond, cut it in half, and then that tells you what each half was made out of basically. So we were given the aldehyde used, and we know that in the final product, it's going to translate to the alkene and a methyl and a hydrogen sticking out. In the final product, the left side of the alkene gives you the methyl and the hydrogen sticking out. So we know that part came from the aldehyde. And then now what we're concerned with is finding the other side. And now that we've like assigned that to the aldehyde, we basically know which R groups were used for the ylid formation. So it's a 3-carbon chain. So it's going to be a propane with a halogen attached to it. right? So we split it down the middle, identified which R groups came from what, and then we just like fill in the blanks basically. So you could like start all the way from the beginning from an alkyl halide, but I think it makes more sense to me if you just like go in order. So now that we have the alkene, I'm gonna separate it into aldehyde and active ylide. And then from the active ylide, I can get the alkyl halide really easily. So for the ylide, I just take like the half we chopped off and then I put a PPH3 on the side of this alkene. So cut off this R groups, replace it with the PPH3. That's your ylide you use to make the alkene. And then we have our propane. But this ylide is only a thing after we activated it with NaH. So what came before that? Huh? The carbanion after the base. Like we made the carbanion this stuff. So it's this exact alkyl group, but instead of the PPH3 that's double bonded to it, I'm just gonna take a random halogen and put it there. So I'm gonna like isolate this carbon chain. And then instead of the PPH3, which makes it the ylide, we'll put like a, I don't know, bromine on it. So now, if you remember, the first step of ylide formation is to take a triphenyl phosphate and give it some kind of alkyl halide. So what you can do is take the phosphate, attack with it in SN2, and then get your inactive ylide. So in this first step, you got your inactive ylide, then you gave it NaH to deprotonate this carbon right here. Then that deprotonation turns it into the active ylide. Then you give the active ylide your aldehyde, and then you get your final products. That is a question, I don't think he really likes it, but it's definitely in the test bank where you will have to like retro synthesize your way back to the beginning here, where you need to find the alkyl halide used. It's fine, you just have to chop this in half.
With the NaH, I'm blanking on how it reacts.
So after the first step, you get whatever R group you had, and now it has the PH3 attached to it, right? This is not going to react with anything because it's just not reactive. What we need to do to make it reactive is make this carbon right here nucleophilic so we can get the square transition state. In order to make it nucleophilic, you take a strong base and just go ahead and deprotonate it. So now you have a carb anion. With the carb anion, you get this reactive form. So now when you kind of line it up with the aldehyde, this nucleophilic carbon attacks the electrophilic one, oxygen attacks phosphorus. Everything lines up and it's able to react. If we didn't deprotonate it, that transition state would never happen. And that's it, that's Wittig. And same thing for Horner, Wadsworth, Emmons. The only stuff that's different is the stuff attached to the phosphorus. Okay, that's it for the handout. We still have a few minutes though. If you have any questions, I'll be here for 10 minutes.
Will be still be available like for us to check later because it is the very first part.
The answers? Yeah, I'll post them.
Okay.
Should we